Where did I put my notebook? Okay. So we have this, there's this domain type, devs.com, devs from definitions, and this, what we said in the very first talk was when we're executing these battery nets, and somebody fires this transition, and we have some function that labeled this thing with some sort of, with a type. What I meant is not that it's labeled with a function or anything like this, but it's labeled with something that I can later turn into a form, into a SQL statement, all kinds of stuff like this. So I need a type, but it should be only finite stuff. Finite terms, I think. Finite types.
Is it allowed to be recursive, the type?
Well, that's one of these subtle things. So for now, yeah, but in a blockchain setting, you might not want this. All these infinite things. If you
no, but finite, but arbitrarily.
Yeah, so like a list is a recursive type, and there might or might not be, it might be a bad idea to do, there might be other ways to do it, but that's sort of a clean star thing. So either you want to use recursion, or maybe you want to use something in your language that can do this recursion, but I don't know how knowledgeable enough to figure out the right way, but I think it will be clear. So, so that's this idea behind this type list, and why do I, if you look, there are existing things like this. So you have XML schema definitions, to name something. You have JSON schema. There is protocol buffers. I can go on thrift. There are a ton of things. People always run into this problem of I have some data in a type that my programming language understands, and I need to serialize it to bits. And then from bits I need to go back, reflect it back into my type. All programs, programming language needs something like this. However, most existing libraries like these, they don't really appreciate people programming in Idris or Haskell. So it's typically, if you look at JSON, JSON says we could give kind of a very like Haskell-y, like let's say you define JSON, it's either a string, or it's a number, or it's a list of one of those things, or it's a dictionary of one of those things. That's it, more or less. So this is all you have, and then you need to work with these things directly. But then I end up, let's say my person record, I'm constantly mapping from a particular JSON thing into my data type of people, persons. You keep writing a lot of this code, and it's really annoying. Furthermore, it's not really, doesn't translate across different languages because JSON schema, so that's a way to say I'm going to restrict which terms I can write into my JSON thing. This is pretty rich. You can say I want to have lists of length between 0 and 5 and all that stuff. So if you want to reflect this easily into Haskell, like how do you do it? You can use refinement types or dependent types. So this is not so obvious. So these things are way too rich if you want to do mathematics with it. And so a lot of, initially we started with using just JSON schema because you can turn this into forms and you can use something like the list, like a string length restriction as a restriction in your input field in your form, so that's pretty nice. But that's in a way just metadata or something else. But it's also, it makes it a lot of work to port this to the different languages. So I want to have a JSON schema parser for all the different languages that you use in your system. There's a lot of work to keep implementing this very rich thing. So we started breaking this down into the bare minimum of features that we needed to be able to still give sensible type definitions. So what do we need? We need an empty type, so that's a type that doesn't have any terms. We need a unit type that has only a single term. We need a product of those things, and we need a co-product. So this is a choice, it's either, and this is a pair.
So you need a complete co-complete category.
Well, that's your terrain. It's probably something that you've all been studying for ages now. Just doing like
so that would mean limits and co-limits?
Yeah, fine.
But yes.
These are limits and co-limits, plus and times.
It's just finite products and finite co-products.
Yeah.
That's not the same as completed covenant.
Oh yeah, okay, yeah.
You
Sure.
can't make all.
No, wait. If you have a terminal driven product, don't you have pullbacks?
No.
No, the other way around.
Okay.
If you've got
Pullbacks and terminal your products, yeah.
and your whole limits,
Yeah.
So
So you sure you don't want pullbacks?
I'm not sure. Like I hope you'll be able to answer like what's the right way to do this because we're struggling a little bit with it and it's pretty
so it might be nice, by the way, you might consider it because people do this kind of grammar all the time,
Yeah.
but they don't tend to do pullbacks, but pullbacks can be very reasonable. They do equation to find subsets.
Yeah.
It could make sense.
So this would go in the direction of let's say refinement types, right?
Yeah.
So that's one direction we've been thinking about, but it's a little bit subtle and it's complicated and I don't have enough other background to do it. It also looks a lot like polynomial functors.
Yeah.
We might want to have Pliny star.
Mm-hmm.
So let me just give you a little bit of examples what it would look like.
So 1 star is the type of natural numbers.
Huh?
1 star is natural numbers.
Yes. Well, let's just write down some definitions so this is a little bit
I'm
clearer.
going to
I
have
mean,
to try and
it's
convince
video-
you to stop saying Pliny star.
Huh?
Stop. We might have to try to stop you saying Pliny star.
How do you say it?
List.
List.
Or
Yeah.
algebra, inductive type.
Exactly. But so let's give a bunch of definitions. So let's not forget this guy. That's why it's not in the braces. So how you define this in the things? Let's define a bit. Like I say, bit is a type. So this is not like a Haskell type. It's this type. And then I say bit equals 1 plus 1. So, but I might want to be able to give these two different branches of this choice a name. So I'll call this, let's say, true, and I'll call this one false. So we have this, but this is just metadata. Then, depending on your view, you could say person is a type, and a person is a name, which is a string that I need to define, times a gender, which could be a bit or something more general. So this is like records. And what we want to do is we want to reflect this into a Haskell data type definition. Any other way around, we want to take a definition and zero that. So in the end, let's just do the list. No. So what we're looking at is you kind of get these trees of a plus node maybe, and then it says.
Yeah, before you continue, probably using another Sharpie would be better for the record.
Yeah. I'll.
Yeah, I know it's annoying.
Right, so you get these things, these kind of trees. But since these things look a lot like polynomials, and we might be able to put a polynomial in normal form, and then we can put a hash of this tree. So we have some sort of hash value of this thing. Now we get an identifier for a type as kind of a global identifier. I just write down this type definition, and now I have an address for this person type that anybody, regardless of their programming language, can use. And we need something like this because we need to compute hashes of these things all the time, because that's what all this blockchain and stuff works on. We just need, for every data finite term, we need to be able to compute a hash. To be a little bit more precise, what you want to say is, I have this function, let's call it ty. It takes a type definition and gives me a type in my language. So this is, let's say, a type in address, and this is my type definition thing. And then I want to have a function that says encode, that takes t, the type definition, x, the term of type t. So I reflect this thing in there, and then it gives me bit string. And then I want to decode. So I give you you give me a bit string, and I give you a dependent pair of a type definition and the term x of type t. So this is kind of all the stuff that we want. But then you might want to have the thing self-descriptive. So I can describe TD in itself. Because I need to serialize both the definition of a type and terms by a certain type. But it's not too hard, at least for if you just have this thing. So what you do is you say TD is a type. Now I'm in my lowercase type, so now I'm in my type definition language. So we can say TD, well it's T0. Let me actually use color. Let's say this is T0, T1, T product, or T code. These are just the labels. And then the other color is this thing, or that thing, or that thing, or that thing. And this is 1, this is 1, and this is TD times TD. So this describes, this is a self-descriptive thing of that thing. And now I can serialize this, probably using this thing to do. So this is a...
But now you need recursion.
Yeah, and now you need recursion. So you need to add variables here and recursion. So, for instance, to do list would be a type to type. So list of the same type of things. So list A then would be either it's the empty list, color-coded programming on whiteboards. It's either the empty list or it's something put in front of the list. So or the empty list, which is the term unit type, or bonds, which is A times list of A. So this is a recursive type, and so this is where things start getting subtle. I'm just gonna dump a few ideas of this thing onto you, and then next few days I hope you can like straighten it out and say, oh, this is just a co-complete category with something. The idea behind this is that you have this judgment of a term T being of a certain type T. And this is very close to having an instance of a certain process. So what I have in my head is that what you could do is for every type, there's some sort of map that gives me a process such that all the possible executions of the process is isomorphic to all the possible terms of this type. Right, so Boolean as a Patriot could be, for instance, this thing, true, false. List is just this. So it's a little bit subtle, but I think there is probably something very trivial going on here that I probably think you might be able to explain. But once you have this thing, what you could do is you can now start considering everything to be a process. And if I have a process that has a hole over here, like a boundary of some type A, which is now expressed as a finite thing, then I can glue it with a process and whose trace will give me a term of this type. So this is a process that maybe if it expects a Boolean, the input would be an execution of this Boolean process, either true or false. Obviously you're not going to execute the process, you just pretend it is a process. But that was one of the ideas behind this thing, and this seems useful or might be useful for this nets within nets situation.
You might be able to get function types. So function types will be hardly impossible, but you might be able to do it if you have some kind of high-order process calculus. Processes can almost operate well.
But I actually want to avoid function types. Not that I don't want to pass functions around, but I want to have these things that I can serialize. And I just want to say that instead of having functions, all my functions are going to look like something like this. Right, so they're all going to be these A tensor B tensor C to E tensor F. and I'm going to be gluing these guys together, which are obviously transitions. Right, so I can think of a transition as running a function. But then these things shouldn't be functions because otherwise stuff starts getting really, really weird. But it's mainly to serialize stuff and to be able, I mean, I had the decode and the encode here. The main reason is that I want to speak of a term as a bit string and be able to give it a hash value. So that's the main purpose of this, and to be able to reflect into these different systems, but completely language independent. This has almost nothing to do with this project, besides the fact that it's so restricted that you can still use it for reasoning. And it's something that I think the entire industry would be very happy to have, because simply JSON schema, XML schema, these things don't cut it. People add features to it, and if you ever want to prove something about it, it becomes horrible.
You want compatibility with JSON and blah blah blah?
Yeah.
Because in that case, I suppose you are not entirely free to define these as you please, but you have somehow to lie in the intersection of all these other ways to do things.
Well, I
For
don't.
instance, if we add pullbacks to this, it's not given that you can represent them in JSON. So you risk to have something that makes you lose this mapping because there isn't an equivalent on the other side. So let's suppose that JSON can do
It's not one-to-one. So this is my Idris implementation, right? But you might also want to say, for TD, I go to JSON schema again.
Yeah, exactly.
But I don't need to go back.
But that's not the point. Like let's say that in TD you have pullbacks. Okay, we want a complete category.
Yeah.
And let's say that JSON is not powerful enough to represent this kind of information. That arrow can't exist because every time you use a pullback on the left, you are fucked on the right. You don't have anything to do that. So somehow you have to get. You are not free to define TD as you want, but you have to somehow to lie in the intersection.
It's a bit strange. You're saying there are these people out there who don't really know what they're doing. We've got some very good practical intuitions. You've got some sophisticated mathematics on this side.
Yeah.
We should not restrict ourselves because they sort of, easy technology out there isn't capable of.
No, but the point is, if you need these to easily, seamlessly communicate with other languages, you have to take these into account. I agree, it would be super nice to be absolutely free to do everything like according to nice mathematics, but it may be, I don't know, but it may be that then you lose that mapping, and then you have to be very careful when you use TD. It's exactly what you want to avoid.
Yeah, so it's really, this is a practice in being sort of like limited what you want to do. And it's very easy to just add an arrow to it, and now I can do all kinds of crazy stuff, but we don't want this because a lot of languages don't do it. So this is a very minimal setting for sure. Refinement types might be, or pullbacks, might be something to add or to not add, but then we should go into detail and look at what we're going to do. So for instance, one of the things is if you rewrite a query. So this is why it also ties into the logic programming things. But so suppose I write like a query, I don't know, I query Elasticsearch. My Elasticsearch query has some sort of type. If I restrict it to be able to write some restricted set of queries so that I can get a type like this, then I can get my results from Elasticsearch. I can maybe turn this query into this general query into an Elasticsearch query, into an SQL query, and into something else. All these things reflect to the same thing, and then here I can just return them together as a tuple, and you're in the same language, and now you're seamlessly talking to different systems.
So this 0-1 product and co-product, you feel that every language uses it, and that's the point.
Yeah,
there's global hash.
You have records, tuples. You might say, like, I mean, I could encode it. There are many ways to encode this in JSON. I just want to have a way to be able to for all the languages out there, you already have things like JSON schema and XSD and all that stuff, and that's great, and they are served pretty well by it. But there's not an equivalent thing for the type languages. There are some stuff that is specific for Haskell or whatever, but I don't get a nice data type definition out of a serial data I got from disk and be able to reflect it into some Haskell thing. So when you're working with protocol buffers or things like this, like a large part of your code is mapping that deserialized thing into the protocol buffer data structure and then mapping that to the particular thing that you're working with. And this really doesn't.
So, correct me if I'm wrong, but isn't products and terminal objects enough to do layer theories? And then basically all the classic algebra that we have.
You
So
can also do it
implement
with
a shitload of stuff with those two things.
But there's no equations in this, right? You can state what it means to be a layer theory, but the power of a layer theory is
Yeah,
to
it's the
equate
diagrams. I
forces.
don't know how to translate diagrams from one side to the other. Yeah.
So there are a couple of ways to do this, but I want to throw it out there. It looks like one of the questions is if it's polynomials, that's pretty nice. Like using polynomials as a schema language, that seems like something useful to do.
Let me give you some keywords.
Yeah.
So the first keyword is, we call this a universe.
Yeah.
That's a good keyword. Another keyword is containers.
Yeah. So it's
Container is a polynomial functor.
yeah.
And you're basically looking at very restricted finite containers.
Yeah. It's something like that. So there must be a good.
And the third thing is a reference. There's a paper called The Power of Pi
Yeah.
by Valtus Stisler,
Yeah.
and he's doing exactly this.
Right.
If you want to look into that.
I think I glanced over it at some point. Anyway, that was that. I don't think I want to say much more about this right now. Other than maybe, if you think about it as a polynomial, that we know that 2 times 3 is 6. And that's right. Yeah. I don't do this often. But but if I think about these things as type, this would be the finite type, the type with 2 elements, the type with 3 elements, and it's the same as the type with 6 elements. Well, it's not the same, but it's at least it's isomorphic or something like this. Now, if you write this as a polynomial and you put the thing in a normal form somehow, and then the question is, what's a good normal form for polynomials that's also efficient to compute? But if I do that, it's like rearranging the tree in a certain way, and then you compute the hash. Now that you have the 2 isomorphic structures get the same hash, that is really useful, I think.
Oh yeah, that's super useful.
So
It's not really dangerous.
it's also might be really dangerous because now this might be saying something very different than that.
But actually, there are no polynomials here, right? There's just numbers. There's no
Well, you
x.
have variables. If you
Yeah,
do
it's
that,
x squared is cubed.
Right, you can have an external variable, but in the schema there's no variables. You could always,
yeah, that's not
reduce
that.
everything to a number.
So that,
If you want initial algebra, you better have actual polynomials.
Yeah,
so I'm kind of.
and
I mean,
that
this-
external variable is not going to.
It's
give
pretty
you
murky
a
at this
form.
stage, but the listing actually has a meaning. You need to include this somehow into your.
Yeah, so
Into
this
that,
list
and
is
if you
not
wanna say
really.
That list becomes list, and if somebody's speaking about this list, I might as well just hash this name or make this name the identifier. I mean,
Yeah, but that's sounding patchy if you do.
huh?
Can you have...
Yeah.
Yeah, so you don't want it patchy, you want it formal. So yeah.
So I mean, this is pretty murky, but yeah, I just wanted to dump it. There's
There ever be non-equal polynomials that have the same initial algebra? Does that ever happen?
Of course.
Does it?
What do you mean no equal?
Like polynomials which are not the same polynomial.
well, I mean, you have Riemann's theorem, right? That's a great example of 2 currently equal polynomials with a different description.
Would you accept the following definition? F of x equals nat, and f of x equals 1 plus x. It's a cheat, I know.
So how are you envisioning this being incorporated?
Whenever you do I/O with this system, you have your definition of your interface in one of these things. And so if you do it in your whatever language you use, you ask for the interface, and its methods are described using one of these things. And so I can automatically reflect this into an API, and you can call it in a like more structures. You don't need to go like on etherscan/push transaction as we saw yesterday. You just put this hash in. I'd rather have a form there that respects whatever particular method I'm gonna call right now. Yes.
So can you, if we have this thing, can you also use this to annotate patroness transformations and places? And so
yeah, that's what you use it for. So you label the transitions with these things, and later you label the places.
Exactly. So you use the general patronet to represent some process, and then if you decide that this transformation has to basically use some JSON stuff, you can just project this into the JSON equivalent, and you don't have to manually do this every time. But you just have a universal recipe to make the patronet formalism compatible with nearly all the kinds of data structures.
Another thing is that if you have this 0, 1, plus, and times, you can use this construction for other things as well. You can use it for composition and tensor product instead of plus and times.
Yeah, obviously, interpreting them in different environments give you different interpretations.
Yeah.
So they can be interpreted as summon multiplication or as a logical connectives, for instance.
So for now, I mean, we can get away with just saying, I label. This is the point. If I label, so in step 1, you label this transition with the type X. Then in step 2, or we didn't talk too much about it, like step 3, let's say I label these two places with the type A and B. And then I have this thing, let's look at this. I label these things with types. So I'm not talking about which, I guess, universe I'm using for my type definitions right now. But if I want to then label this guy as a function that is A times C to B, that means that I need to have at least this thing in my
Times or plus?
times in this case, because it's this would mean that it gets a term of type A and a term of type C.
Okay.
So this needs to be times.
I'm not sure if long-term the analogy between, well, maybe if you just keep them really general abstract operations of times and plus, but like the difference between tensor product and composition is very different from like product versus code product. So I don't know.
Yeah, so maybe that's split the uses, but the reasoning comes from that if I want to go this 1 to 3 method, and I want to give you, say like, for every transition, first I label it with the types to record these messages, and then later I'm going to label it with functions that follow along with this net. Then they need to have some sort of input-output thing. So that means that if the product of these two things should rather still be a type in my whatever universe I pick. So you need to have at least times. And then if you want to destruct on these things, like you want to use it to make a choice, you go left or right.
You got a cool product.
Might include one have a co-product. So,
But you could keep these external from the universe, right?
yeah, I guess.
That time does not need to be internalized. You could just keep the A and the C in your universe, and then afterwards you form the times. But that's in the real world. That's an actual time.
But I think you want to internalize it if you want to project this easily to some other language.
Yeah. So it's gonna get, this function is gonna get something. I mean, there are different ways to do it. You could keep it external, but I'm just saying like it kind of led to this situation. This is more if you would want to fold everything up into one wire. It's not a place. Then you could have a wire which expects something of type A times B and then type C. So it looks like a single wire, but there's actually type value running over it. And it seems like once you have products, you can keep doing this with nets. And you can have a net that makes a choice. You turn something of type A plus B goes into this thing, meaning that in here there could be two transitions that fire depending on whether it's A or B.
And then if you want, you can explode it and get back that definition.
But so for now, we've been kind of avoiding to deal with this properly by just saying, oh, you can't do anything with X, but I have some sort of operator like this, which is specific to the Reacts I'm using, and then we just use JSON schema and define the thing for JSON schema. It kind of works, but it's not so nasty because not so nice because we're really going inside this.
I suppose this is very interesting per se, but to implement it in the Statebox stuff, we still have to work on formally define the Statebox stuff up to now. So we still, I think there is still quite a lot of work to do to make whole SpectraNet business as formal as we require. But I agree that this is something we should reason in parallel and try to merge these two things.
So have there been, surely there have been projects like this before that are about inter-language.
Yeah. So things like, well, but typically they don't consider all the really actually typed languages. Like, so there exist these things like protocol buffers and thread, but I cannot read, there's no real thing to say like give me two protocol buffers as a term and then combine them into a new protocol buffer. You can do it in the language itself, but they don't really become like first-class citizens of your language. Whereas where I can just say either is pair of A and B, and I'm like doing the product thing, and then if I can reflect that back into a definition.
Also, I suppose that even in the most optimistic scenario, there will always be protocol buffers that are not compatible with this.
Yeah, I don't need to go back the other way. I just need to, right? I don't need to reflect every protocol buffer into a thing like this.
But
I don't want to consume stuff like that. I want to be able to tell you I need a term of this type, and you can specify it in JSON or in XML or in whatever. But we just want to, the main thing is that we want to be able to construct, like do products of types or better match on products of types.
What I mean is that there may be
forms and stuff like that.
protocols that are not compatible with this. So you say I want a term in, you say JSON, but imagine something else, and a term in imagine something else, and you don't have a way to translate that product in that something else. So in the end, I don't think we should really aim for total universality,
No.
as long as we cover a decent subset of the most used.
I think plus
protocol
times
buffer
is enough, and may or may not something like a list or links or if you want, how you want to do it. And I'm not sure what the best way to do it is, but the best way in this thing is for this is so that you can use it later on in all your proofs and so on. You don't have something super complicated to work with because just typing out JSON schema in Coq and you're like a year.
Can I ask a question?
Yeah.
So, if I understood correctly, you're doing more than encoding types, right? Because you've got this translation of
Parsing.
of computations into petronets, right? So this petronet is something that takes some type and produces a term of another type.
Yep.
And when you chain these petronets, you've got this kind of like a skeleton. These are more than types, right? These are kind of witnesses of some computation that's gone, that's been performed. And that's what you're interested in, right? You're interested in these kinds of sort of I don't think these are types anymore, right? They're kind of like a trace. It's like a computation trace in some sense.
Yeah. So it's like this distinction between an algorithm and an actual protocol. So I think you have the static stuff, data that's fixed, and then we can encode and decode and nothing weird happens. And it has a canonical encoding that gives you a hash for a term, and the same thing for types. You can reflect between those things. But then you glue them together into functions, and these petronets then form the skeleton for it.
Yeah.
So like in CPN where standard ML is used, which is a subset of, CPN ML is used, which is a meaningful subset of standard ML functional programming language.
Yeah.
You have this very expressive type of petronet, which turns into like a programming, a visual functional programming environment.
Yeah.
Where the graph aspect is the first citizen.
Yeah.
And so I could imagine, I mean, okay, that's standard ML, which is used in CPN.
Yeah.
But why not have some sort of petronet version instead of CPN? Maybe think about how to use Haskell.
Well,
I
so
mean,
that
does
is
exist,
the thinking. It's very similar to CPN, but you want it way more restricted because you want to use it in these settings such as blockchains or maybe compiled to hardware or whatever. So you need a more restricted version of it. And this is the equivalent of a very restricted data type definition.
I mean, the thing about CPN is that you can develop these modules, so it's comparable to components where you have strictly defined input-output states, and then you can just hierarchically nest non-atomically lower level hierarchies as many as you want.
Yeah.
And then study brilliantly all sorts of concurrency conflicts and abilities in highly distributed systems.
Yeah, so what I thought is to do something similar to these modules in CPN. Probably the way you want to do it here is use something like Protoquipper. You probably know this language, which doesn't allow you to express like all the programs, all the expressions in a terminate. It's a language to describe, let's say, I want to have a token ring with 4 players, or a token ring with for all n, it gives you a petri net of a token ring of n participants. And then this Protoquipper expression, if you evaluate it, it would go into one of these things. But everything needs to be finite in some sense. For this,
Protoquipper
to
is
be able to be useful.
programming language for monolevel categories.
Yeah, but so you can use it to write programs that generate diagrams. But the programs that generate your diagrams are not things that will run infinitely long. I'm sure that they terminate within a certain number of steps, and this is very important because the entirety of your system needs to be able to do that.
But that's because it's a programming language for monolevel categories. A string diagram can be infinite. That's exactly the point.
Yeah.
It's like your semantic will never learn. Your semantic doesn't allow you to do infinite string diagrams.
No, but you could have a program that runs very, very long and in the end gives you a finite diagram. But the point is that your execution of this thing should be beforehand. I cannot allow a halting problem, right? Anywhere in your entire stack of a node running one of these blockchain things.
Yeah.
So I can say I had gas, but it's actually Ethereum.
Don't know enough about Protoquipper.
The other thing working with CPN is so the graph aspect should be like the first citizen, and CPNML is in support. You add that to the arcs.
Yeah, the guards.
Yeah, exactly.
Yeah, so that's.
And the thing is, you have done this combination on the one hand side, the graph aspect of state transition optimator, but then you can also work with the functional programming aspect.
Yeah.
But if you go wild and overboard on the functions, then you swallow a lot of the state transition graph semantics into the functions, which defeats the purpose of CPN. So let's say you want to maybe think about using some other functional language like, Haskell or so, you would have to figure out how to meaningfully create a subset and then support that in some new version of.
So I wasn't really going to mention it that much, but do you know what guards are in PetriNet? So you have if there would be data inside the token, in this situation, both these transitions would be enabled. But now I can put a function on here. So if this is something with A, then I put a function here from A to Boolean. And for each token, if it's true, then it will kind of be sitting on the wire here, and only then will the thing be enabled. But now the question is, how are you going to do these deadlock analysis and likelihood analysis? Because you need to now consider your guards and all the things that led up to this A. And so now you need to do totality checking and all these things. So your functional programming language that you put on top of this, and your schema type language needs to be very restricted in order to keep doing your analysis. In many cases, you can get away with guards for very restricted processes, and so in practical terms, it's a matter of finding customers or use cases for very restricted language without guards and without recursion and blah blah. But this is why this stuff is relevant.
The other very practical hands-on statement here is if once again you go wild on the functional programming side, then you have these parallel algorithms like in splits.
Yeah.
Okay? And then, because like in CPN, the functional programming aspect is minimalistically supported because the graph aspect should be the first citizen. So if you really go wild, you don't have the tools in CPN.
No.
When you have some mega function on one branch and on the parallel branch also mega function, and they somehow get into a mess, you don't have the tool support to actually figure out what's going on. So I always tell like my students, when you do the mini projects in CPN, please be careful with how much CPN ML you actually employ.
Yeah, as little as possible, because at some point it's just no longer possible in all cases to compute these, to do these analyses.
Yes.
That's exactly what you want to avoid. So I could say I'll just put Haskell as a programming language and I'm done. But in a blockchain setting, that's not going to be the best thing to do. So just to go on to this for one moment, it's a bit of, suppose you have two tokens here, and I'm going to color them now to distinguish it. So this is I don't know, somebody's thing, and this is somebody else's thing. And this token is consumed. I fire this one, maybe, and this goes here, and it goes there. And then this is some person saying yes or no. And this is another person saying yes or no. So now suppose this guy does yes. So this thing ends up here. And then this thing is fired. So we get this one here. And now these things are picked non-deterministically. So suppose this guy says no, but it picks this one. End up in this situation. And now I join again. So the net does this, and I say now case closed. But now I mixed up two persons' cases, because this was supposed to be green only. So one way to do this in these CPN tools is that you say, I have a guard on here that says something like only allow tokens if the color of X is the color of Y. So that you only get these pairs like this.
Exactly. So you introduce the lifecycle ID color for a token.
But the problem with this is that it's of course exponential in the number of tokens that you have, because you need to consider all pairs. This is like a database join that you're doing here. So this works for bounded nets, and if you can prove that your net is bounded, then you can say that this thing will go. But if I write down a guard here and I'm doing a process where I have 5 million tokens here, I basically effectively block blockchain from processing anything.
So do transitions just consume any tokens sitting in? Is there any?
Depends on the guards. I mean, of course, there's also a weight on the arcs.
Yeah.
So it might be. I mean, it depends how you program them in CPNML those arc statements, the guards. But you can say maybe transitions only enabled if an input state has a weight of 2 tokens of a particular token color.
Yeah.
Right. And only then, but the important semantically is that of course all input states must have the required and specified token amounts with corresponding color.
Yeah.
To enable a transition, then all tokens get swallows.
Yeah.
And then unless you have a delay, I mean, because you can time the color patronage too, so you can introduce some sort of delay period or whatever, but otherwise you get immediate output of tokens again corresponding to what you program onto the arcs.
But the problem I would say with like CPN tools, so the ideas are really nice, but it's way too rich. So it's very rich. It's that's a problem, because at some point you can no longer do reasoning about it. And so while this is very much in the same tradition as called battery nets, but then in a way where we keep an eye on remaining total or remaining able to prove livelihood, things like this. So you can just leave guards out, and you can actually leave color out, and a lot of things, and you can still do useful stuff if I'm able to distinguish 2 different executions of a net. Because I could have just said, well, why run these 2 things in one net? I just have one execution, I have exactly the same net here, and it's another one. And so that's a different way to approach one of these problems. But there's an entire catalog. I can actually share it of these patterns, and you'll see some of these examples and why they introduced these tools. But in my opinion, it's not the best way to just like. I mean, it works in a normal setting for programming, but not on a.
Also, my feeling is that describing what you're saying now categorically is much easier than progressively enriching the pattern and those sort of stuff.
Yeah.
That seems a much cleaner way.
I would say that one of the problems that I can see with this kind of CPN approach is that it's very expressive. But if you want that compositionality, then you have to work much. I mean, I don't know if it's possible.
No, just Guards by itself is already hard.
If I understand correctly, I mean, you have the modules.
Yeah, you have modules, but that doesn't necessarily mean, so you can compose things from small pieces.
And you can
but that doesn't necessarily mean compositionality in my sense, right?
Okay.
So I don't want emergent behavior, I want to understand the behavior of the entire thing, just by understanding the behavior of the component pieces. So the problem is that these sort of languages, you get the emergent behaviors because essentially this algebra, these algebras are not compositional.
So maybe the other thing is also very practically state space explosion. So when you then do your model checking, and Impulse creates your state space, and say, I mean, I ran into this. I told you with these life cycle things, and there's a certain number of nested components. I mean, modules actually.
No, that's exactly the thing. What Paul is trying to avoid with doing this composition is so you don't want to do state-based checking over the unfolded thing.
You weren't here when Paul gave his talk, but with this categorical model, you basically you can write the state space compositionally. You don't really want to.
Yes. So I mean, I can't do the state space analysis for the entire life cycle. It's completely possible.
Yeah.
Because the state space is so enormous. I then have to do then meaningful. I mean, I can then only focus on one component if I'm lucky, because each component again just breaks up into.
Instead, in this case, if you can decompose the network in a clever way, you can.
Yes.
So you would be probably super interested to look at the register code that exactly about it. You will be like,
yes.
This is exactly the thing. Like, how do you extend these patternets into richer things with timing and guards and all that stuff while keeping this compositionality? It's not so clear.
It's not so clear, but
and so, in particular, I cannot just say my types are Haskell types. I label my transitions by that. That's not going to work.
Exactly.
So that was kind of the point of this thing. That's already way too rich.
Yeah.
Maybe products and co-products and unit and void is too limited, but I'd rather be too limited for now than too rich.
But I think that in general the philosophy compositionality is more important, that richness in feature is what we should do now.
What?
The philosophy that compositionality is more important than having a rich set of feature is exactly the philosophy we should embrace.
Yes.
So
or put differently, like constraining yourself gives you more stuff to reason about later.
Exactly.
And better behaved stuff instead of being able to do all kinds of things. Let's cut it here.
Okay. Thanks.
Yeah.